Hi, everyone. Thank you for coming today and listening to the talk. As you probably know, hopefully, today I will be telling you about SLN homology, or I will be telling you how SLN homology, obstructs prevent concordance. Right. So before I begin, I want to point out that this is a project that stemmed out of WisCon 2019. So WisCon 2019, WisCon stands for Women in Symplectic and Contact Geometry and Topology. And this was a project that was initiated jointly with Melissa Zhang. I'm going to get all the names out of order, so I apologize. Nothing here is alphabetical. Carmen Caprau, Christine Lee, Radmila Sazdanovich, Adam Lawrence, and myself. So what I want to tell you about today is namely just one theorem. I want to explain one fact, which is the following. So the goal is to show you how if you have some ribbon concordance, let's call it C, then let's say from L0 to L1, then the induced maps on SLN homology, let's say on SLN homology, let's call them HNC from HNL0 to HNL1 are injective for all n bigger than or equal to 2, right? So this is named basically the theorem I want to talk about today. And before I do that, I want to point out that this is an extension of something that was originally done by Zemkin in 2019, right, where the idea truly stemmed where he did it for not for homology. Then shortly thereafter, he and Adam Levine extended it also in 2019 to combinative homology. And then we later on, Kang actually truly generalized this or extended this a lot more for a lot of other contexts. Great. So what we're going to be doing is basically we're going to be using the framework of Zemke and Levine and Zemke to just directly extend the results to SLN. In particular, universal SL2, universal SL3, and then SLN. Great. All right, so before we get there, I want to just remind you of a couple of facts from SLN homology that we will be needing. So we need the following 3 facts. We need to remember that for SLN homology, we have, first of all, the certain properties known as the neck cutting relations, right? We have the sphere relations. Right, these are both local relations that allow us to decompose one diagram, foam, or cobordism, however you want to think about this, into a sum of other foams or cobordisms. And lastly, we're going to use the fact that the functoriality, that these homology theories behave nicely with respect to concatenation of diagrams or of cobordisms. Great. So SL2, just as again, this is probably known by almost everyone, if not everyone who's listening, but just to remind you, the relation states the following, that if you see a cylinder, right, or a neck, you can slice it, you can cut it right in the middle and decompose it as a sum of caps and cups, where you allow for certain dots in particular, one on top and one on the bottom, and then it's universal because we are allowing certain parameters to show up. And then the one with the parameter, A is some, in the universal case, some indeterminate parameter that we're not specializing to anything, then you get some extra piece that has no dots, right? And then the sphere relation is going to tell you that if you see a sphere with no dots, that is 0, whereas if you see a sphere with 1 dot, that is 1, that evaluates to 1. SL3 is going to be very similar, right? SL3 is going to tell us instead, well, you have a minus sign because it's SL3, so it's slightly different. But once again, you still evaluate into a sum of, caps and cups. Right, but the point is that here, instead of having just 1 dot, we're going to interpolate between the number of the ways that you can add dots to the top and the bottom, right? This is what we're going to call it. If we're going to, this is, for the sake of argument, let me just call this F. Then this is what we would denote as F2, 0. This would be F1, 0, and this would be F0, 2. This notation will be used later on, so just as a reminder, I'm introducing it now so that you know what I mean later on, right? So the 1 and 0 is just really telling you how many dots did you put in each component after you cut its neck. And then, of course, that's not all. There's a component that has to do with the parameters that come with SL3, right? So we have 1 dot here, and none, and then none on top, and then one on the bottom, and then the last piece that has to do with the SL3 bit, or the B bit. Great, that carries no dots. And then lastly, and then the sphere relation here is going to tell you that if you have no dots, or if you have one dot, that evaluates to 0. But if you have 2 dots, you evaluate to 1, or sorry, minus 1. And then lastly, of course, you have SLN, which we can just, and this is for n bigger than or equal to 4. Right. For SLN, our net cutting relation is going to be the following. So you're just going to, again, interpolate between all ways of adding n dots. So n minus 1 minus I dots on the top and I dots on the bottom in such a way that they sum up to n minus 1, right? Where I ranges from 0 to n minus 1. That's the net cutting relation. And then the sphere relation, as you no doubt either know or expect, is going to tell you that if you have I dots here, then this is going to be 0 whenever I does not equal n minus 1. And it's going to evaluate to 1 whenever I is equal to n minus 1, right? In agreement with the previous constructions. Okay, great. So that's pretty much all we need to know about SLN homologies. This plus the fact that they're functorial and behave nicely with respect to just concatenation or placing concordism side by side, that evaluates to taking the tensor product. Great. So then go back to our theorem. What do we need to know in order to understand this? Well, what is a ribbon concordance? So let's maybe go through and actually define what that is. So first of all, what is a ribbon knot concordance? So a knot concordance, so between 2 knots, K1 and K2, is viewed as living in S3, is a smoothly embedded annulus in S3 cross 0, 1. 1 second, sorry. Yeah. In S3 cross 0, 1, whose boundary given by K0 cross 0, 1 and K1 cross 0, 1, right? So it starts at one knot, ends at the other. That should be, I apologize, 0, 1, 1, of course. It starts at one knot and ends at the other. Related to this, we can define the following, that an n component link concordance then, right? So between 2 n component links, so this is important, right? Both links have the same number of components. Component links, let's say L0 and L1, is the disjoint union of n knot concordances between the corresponding components, right? Between the corresponding components. Fantastic. Okay, so a knot concordance, a link concordance. So it's important to note that if a knot concordance goes from K0 to K1, right, this is just some sort of concordism, then you can think that if you take this concordance and just flip it upside down, you would get some other concordism from K1 to K0. Is that concordance as well? Yes, it is, right? So this relation is a symmetric relation. Fantastic. Now, what is a ribbon concordance then? Clearly something more special. So a ribbon concordance, then I'm going to call it C, between, again, two knots or 2 links, whatever you want to think of this as, so whatever, is a concordance whose projection onto the 0, 1 factor is a Morse function on C, whose indices, so with only index 0 and 1 critical points. If you don't remember what that means, all this is telling you is that your projection or your map, all this is telling you is that your concordance is really just going to have local minima and local maxima. Oh, sorry, local, let me say, saddles. And saddles. So in particular, what this means is that if we think of a ribbon concordance, right, it is some concordance, you start at K0, you end at K1 in the same way that a knot concordance does. You can think of flipping it upside down and getting the reverse concordance, right? And while a ribbon concordance, the reverse of a ribbon concordance is in fact a concordance, it is no longer a ribbon concordance. And that follows directly from the fact that if you invert a minima, you don't get a minima back, obviously, in which case this fails, right? So this is a key point, is that this is not a symmetric relation, right? The orientation here really does matter. or the direction, I should say, of the map really does matter. However, if it is true, then we can say the following. So if such a thing exists, that concordance exists, and we say that, or say between L0 and L1, then we say that L0 is concordant, is ribbon concordant to L1. Cool. Okay. So that gives us the definitions. Now, in order to prove our actual claim, we're going to depend on the same construction that Zemke and then Levine and Zemke used to prove their results. Namely, the fact that we can decompose a ribbon concordance, or we can into a sequence of tubes and saddles, right, and spheres. So how are we going to do this? So let me call this. So this is Zemke's construction. So what does it say? So if we start with some ribbon concordance between L0 and L1, then we're going to let C bar be the mirror of C, right? This is just basically saying take C and flip it upside down. So this is concordance, not necessarily ribbon, right? But certainly a concordance from L1 to L0. Then Zemke's claim is that the composition of these concordances, right? You take one concordism, you flip it upside down, and you glue them together, right? This goes from L0 to L0, can be obtained from the identity concordism, or the identity concordance, on L0 by tubing in, and I'll try to make this more precise, tubing in unknotted, unlinked spheres. Right? Okay, or two spheres. I should specify that. Two spheres. Okay, so how do you do this? Well, the step is the following. So the trick is the following: is you pick a movie presentation in a following very precise way. So pick a movie presentation of C, such that the first move is you start with n births, right? Which is basically just saying you're adding unknots. 1 through un, some particular number, that are disjoint from your original knot, in this case K0, and each other. Right. Your second movie point is the creation of n saddles. Right. So this is, we're going to call them BI, or bands, that are connecting the UIs to K0. And then lastly, our last movie point, our last movie scene, let's say, is a final isotopy from the surgered knot, which is given by K0, right? You union a bunch of unknots, right? That's the birth part. And then you glue in a bunch of bands or saddles, if you want to think about that, to K1. Right, so you isotope that construction to K1. And then, let me write 2. And then what you end up getting is something in the following way. So I'm just going to give you a picture here, because it's easier than trying to draw this. There it is. Apologize, let me just move it up. Ooh, there it is. Right, so what is that telling us? So Zemke's claim is precisely the following. If you start with some sort of ribbon concordance from K0 to K1, right, this is some sort of concordism that has only saddles and minima, no maximum, then you can take this and isotope it so that you can construct some sort of movie presentation that has the following property, right? That starts with your K0, then you have a bunch of births, then you have a bunch of saddles, and doing this, you can join your knot K1, given here, to your knot K0 through some sort of ribbon concordance. That's his claim. Excellent. Now, the second part of his claim is the following, or sorry, that's for the first part of his claim. In order to actually attain his claim that if you compose it, then you can just get this as, you can get this by taking the identity concordance and tubing in unknotted, unlinked two spheres, is best explained rather than by writing it down in words, again, by just looking at the following picture. Let me just bring it up here. Right, so let's zoom in. So what this is telling us is, if we think of this as basically, this is C up to here, this is C bar, right? You're taking this and flipping it upside down. Then, of course, I'm skipping some steps here. You'll notice that these unknots, these spheres suddenly disappeared from this picture, right? So through a procedure that I unfortunately, just for timing reasons, can't really go into too much depth, there's a way of obtaining another cobordism, as you can see here, where this really is, and if you just kind of try to piece it together, this really is the identity concordance on K0. Right, so you end up with, through some procedure where you swap some spheres with other spheres, then you end up with something that really is the identity cobordism on K0. Right, great. So this is his claim, and how do we use this to actually get a result? Well, in order to actually get that, we're going to have to, what happened there? We're going to have to write down a couple of lemmas, which are basically going to give us a result almost immediately. So the first lemma we want is that if we take F, if we let F be, let's say, some embedded cobordism from in R3 cross 0, 1. So I should probably point out, for those of you that are still paying attention, you're probably wondering why R3? Where did my S3 go? Right, this used to be S3 cos 0, 1. The reason that I can only, or I can just generically work in R3 is simply because any cobordism that's embedded in S3 cos 0, 1 essentially is going to miss some segment generically. So it's going to miss some sort of segment of the form T cross 0, 1, in which case I can just isotope everything away from that piece and really just work in R3 cross 0, 1. Right, so all is well. We can just think of everything living here. Okay, so if you start with some sort of embedded cobordism in the space, let's say from some link L0 to L1, and we denote by S of K some unknotted, unlinked two-sphere in R3 cross 0, 1 still, right? We're still working in the same, or living in the same space that is unlinked from F with K dots and contains K dots. That's what that K here is supposed to be representing. Then the following things are true. In particular, if we take SL2 homology, then taking a cobordism and just placing it side by side with our sphere, then that is going to give us 0, right? And the reason for that is that really, right, due to functoriality, this really is just F tensored with H2 of S, and this is 0, if you remember, by the relations that we wrote up here, right? So I'm just going to bring them down, or maybe not bring them down, but highlight them a little bit, right? These relations right here. And likewise, right, so that's 0. So what happens if you add a dot? Well, in that case, our relation really is, so this is H2 of, oh, sorry, this is 0, 0. However, if you do H2 of F union S1, then this is really just H2 of F, because H2 of S1 is 1, right, by the relations that we saw just a little while ago. And likewise, if we do SL3 and SLN, really the relations are going to be completely analogous and are just going to be given by the sphere relations for SL2 and SL3 completely directly, right? So I'll just write them out for concreteness. All right, so in the case of H3, then H3 of F union SK, this is really going to be 0 when K is not equal to 2. And it's going to be minus H3 of F when K equals 2. Right, and then likewise for C, for SLN, if we have F of SK, this is going to be 0 for K not equal to n minus 1. And then it's going to be Hn of F when K equals n minus 1, as expected, right? And then, of course, as I basically told you as I was writing this down, the proof really just follows from functoriality plus the sphere relations, right? Okay, great. What other thing do we need to know? Right, so once we have this fact, we need another fact in order to actually be able to prove our theorem. So let's do another lemma. So what this tells us is, well, suppose we start again with some F, it's some sort of embedded cobordism, some same construction as before. But now, instead of considering spheres, we're going to add handles to it, right? So in particular, we're going to denote by F prime the result of basically attaching a embedded, let's get all the proper descriptions here, an embedded three-dimensional one handle with ends on F, right? So if you want to think of, let's say F is something like this is a terrible drawing, right? We're really just holding a handle onto it. So if you were to do this, sorry. Don't know what happened on F. So if you let F prime be this, then the claim is that, oh yeah, and we denote Fij to be the result of taking F and cutting along that one handle, and then Fij is denoting the pieces that we get, or the components that we get, where we get the different dots, right? As I explained. Ooh, where did that go? As I explained here, right? So if you cut around here, then F20 is going to be the part that you get from cutting the one handle, and then basically getting 2 dots on top and 0 dots on the second component, and so on. Then, if you do that to whatever concordism was with a handle, and you denote by Fij the resulting pieces. So let's denote by Fij the resulting components, dotted components, after net cutting F prime, then, right, we have that for SL2. H2 of F prime is really just going to be H2 of F10 plus H2 of F01 minus A of H2 of F, right? And this really, really does, just like in the previous lemma, follow completely directly from the fact, from the net cutting relations and functoriality once again, right? Minus A, right? And then I'm not going to write SL3, but it's basically analogous, or yeah, analogous. I'm not writing it just because the equation is a bit longer, but it really is just exactly the same thing. And then for SLN, right, we have F prime. This is just going to be given by HN, and recall that in SLN, what is the equation that we're working with, right? It's this one. So let's just copy it and go back. Right, so for SLN, we have this, in which case we denote F, we're going to have an N minus 1 minus I, comma I, right? And we're going to sum where I ranges from 0 to N minus 1. Okay, right, and then stating this, but I will, again, just write it. This is really just functoriality plus the net cutting relation. Okay, nothing too fancy so far. In fact, very, very, very straightforward. Okay, what else do we need in order to get to our result? One more proposition, and then we're basically done. So, proposition. So if we are going to denote, let's say, let's note D by D, sorry for the change of notation, some embedded concordism. So up to now, same construction, D, some embedded concordism. Right, and again, from L0 to L1, so it's the same thing. And let's denote by S some two-sphere in R3, 0, 1. And again, this is unknotted and unlinked from D, right, just like before. And we're going to now denote by D prime the result of attaching one end of the three-dimensional one handle to D and one end to the sphere. So it's the result of attaching attaching one end of a three-dimensional one handle to D and the other to S. Right, so in my completely terrible cartoon, all this is saying is, all right, you take your one handle, and then here you basically glue this here, right? This is S, this is your handle, and then this is your F that you started. I guess in this case we're calling it D. Your D that you started, and this is D prime. Okay, good. So you glue this. Sorry. You glue this, and the claim is that if you take Hn of D prime, that this is Hn of D for all and bigger than equal to 2. And I realize that the cartoon makes it look really trivial, but you need to remember that this is not just living in S3, and that the concordisms themselves can be a lot more complicated than the silly thing that I just drew. Right, and then, I mean, at this point, really, the proof is literally directly follows. It directly follows from the previous lemmas, right? Because it's just a matter of setting F to be D union S and F prime to be D prime. And then in that case, it's completely direct by just applying what you needed to do, right? The net cutting relations and the sphere relations. Okay, fantastic. So now finally we are ready to prove our theorem, which really is just going to be almost a corollary from this proposition, right? So the theorem itself, right, just as a reminder, is telling you, right, if you let's see the Rubin concordance, a Rubin concordance from L0 to L1, then the induced maps on SLN homology So Hn of C, Hn of L0 to Hn of L1 are injective for n bigger than or equal to 2. Why is that statement true? Right? So let's actually just prove it. Okay, the proof. What do? So if you consider D to be, let's say C bar composed with C, right? This composition of our concordances, this is a map from L0 to L1. Then we know that Hn of D is really just going to be Hn of C bar composed with Hn of C, right? This is stuff by contrariality. But however, by Zemke's construction, we actually know that D is equivalent, right, to taking the identity concordance on L0, sorry, I wrote K0, on L0 cross 0, 1, on L0, whatever, on L0, and 2 being in spheres, right? This is these funny pictures that I showed you previously, right? And 2 being in spheres, 2 spheres in particular. So then by the previous proposition, what that tells us is that, so by the previous proposition, what that shows us is that if we take H2 of D, this really is just the identity concordism on H3 of L0, right? And then Hn, or H3, sorry, H3 of D is really just going to be, well, up to a sign plus or minus the identity concordism, or identity concordance in this case of L0. And then likewise, Hn, oh, no surprise, is going to be, of course, the same thing, right? Up to a scalar. So I'm going to call this R, where this is some R in our field, times the identity on Hn of L0 for n bigger than 1 to 4, right? So in particular, what this tells us is that, so this implies that Hn of C is injective, right? And then consequently, and obviously Hn of C bar is surjective. So then consequently, by our previous result, then consequently, this actually just gives you the result immediately. Sorry, I don't know what that was about. Yeah, but moreover, if you remember this, or you know this, I didn't get a chance to mention it, but since the SLN homologies actually preserve the grading, so since you get since Hn preserves grading, this map not only tells you that the induced map from Hn, that this map is injective, it actually tells you that it maps it in the following way, right? So if you take the ijth graded piece of L0, this really is getting mapped into the ijth graded piece of L1 as a direct summand, right? Which is exactly indirectly an extension of the work of Zemke and Lumina Zemke later on. All right, and that's it. Thank you very much for listening. Sorry about the confusion on some of the points and probably some of the things that I said incorrectly, but all right, please ask me questions. Thanks.